Understanding Physics, and this video is for Assessed Practical 9, which is about capacitors. So, summary, basically, charging and discharging. So, we're going to charge a capacitor and we're going to do a graph of voltage against time. And that's all you need to do. This is what I ask my students to do, and it's enough. So charge a capacitor, voltage against time. Then discharging a capacitor, and we're going to do two graphs. We're going to do voltage against time and the natural log of the voltage against time. And from each of those graphs, we're going to get a value for the time constant from each of those graphs. So this is the equipment you need. You'll need a voltmeter, like a multimeter, a resistance box, and then you can change the resistance, and a capacitor. Now I would recommend like a 470 microfarad capacitor, something like that. Maybe a bit bigger, maybe a bit smaller, around there, 470 microfarads. And then if you're using 100K, then your time constant will be about 47 seconds, won't it? RC, which is suitable. Then also a DC power supply, yeah, because we're going to need to charge the capacitor, and some leads. Now for charging, this is the simplest circuit here. If you close the switch, then the capacitor charges up. I recommend using 10 volts. You'll see why a bit later. And a voltmeter across the capacitor to measure the voltage across it. Okay. You start your stopwatch when you close the switch, and I would suggest taking readings every 5 seconds for about 2 minutes, which will be between 2 and 3 time constants. Yes. You could record the voltage with a data logger. Not necessary. Don't panic if you haven't got one. Just do it as a team. Have one person with the stopwatch, and every 5 seconds they say now, and then another person reads the voltage, calls it out, somebody else writes it down. Yeah, work as a team when you're doing this. Make sure that the capacitor is uncharged when you start the experiment. So how do you make sure it's uncharged? Is if you just get a lead and connect it, like short circuit the capacitor, and then if there's any charge on the capacitor, it won't be there, it'll discharge it. Yes. So you make sure the capacitor is uncharged by short circuiting it before you start the experiment. Plot a graph of voltage against time, and you should get a graph that looks something like this. And I would just ask my students to get this graph. Okay. Now for discharging, this is the circuit. There are other circuits that you could use. I like this circuit. Basically, you start with the switch closed, and then when the switch is closed, the voltage across the capacitor will be 10 volts. When you open the switch, then the capacitor will discharge through the resistor. So you start taking readings when you open the switch. And again, work as a team, take readings of voltage every 5 seconds for 2 minutes. Okay, so, and this is for discharging the capacitor. And you should get a graph that looks something like this, a typical exponential decay. Yes. Now, how do you get the time constant? Well, the time constant, this is why we started at 10 volts. It makes it easier. It's just the time it takes to fall to 3.7. And so you can read it off the graph. If you look at on my graph here, you can see it's about 47 seconds, interestingly. Okay, why? Well, because if V is V naught e to the minus t over RC, so if the time is equal to the time constant, then V over V naught is e to the minus 1, and e to the minus 1 is 0.368, in other words, 0.37. So we're getting a value for the time constant off this graph. Also, you plot a graph of log V against time, and that should give you a straight line. Now, if you look, V is V naught e to the minus t over RC, take logs of both sides and rearrange it, y equals mx plus c. So the gradient of this graph should be minus 1 over RC. So if you get the gradient, don't worry about the minus, do 1 over the gradient, that will tell you your time constant. So you've got your time constant two different ways. This is the more accurate way of doing it, because when we do a line of best fit, it's a good way of minimizing the effect of random errors. These are the bits and pieces that we should be doing. The first one, this B, is straightforward. Now, this H, using a signal generator and oscilloscope. Well, we're not, are we? I don't know why on earth that's there. Don't panic, we'll have an opportunity to tick that off later on. How strange having that there. Use of ICT. Now, if you're using a data logger, great. If you're not, then we can tick this off just by doing, if you do your table and maybe have a go at the graphs on Excel. If you do the log graph on Excel, then you can actually get it to tell you what the gradient is. Yeah, if display equation on chart, and Excel is actually telling you the gradient. Okay, and that's that.